Hello and welcome to Workshop 3, Part C. You'll recall in the previous video we derived, using Bohr's postulates, the quantized energy levels for the electron and the hydrogen atom. Just let me remind you the result. The result that we obtained was that the energy in the nth stationary state, the nth state, was given by this expression here, minus 1 on n squared times a combination of constants, which comes out to be me, the rest mass of the electron, the charge of the electron to the power of 4, and 32 pi squared epsilon naught squared h bar squared. Now, this is how it's often written in textbooks, but an entirely equivalent form is to realize, of course, that h bar is h on 2 pi. So when I square that, I can simplify this expression to give an entirely equivalent expression for the energy of the electron, and that comes out to be me e to the power of 4 on 8 epsilon naught squared h squared. So basically we've got h squared on 4 pi squared. The pi squareds cancel. 4 into 32 goes 8. Now that's the first postulate, and let me remind you that this integer here, which is referred to as the principal quantum number, characterizes the energy of the nth state. Now, when we make transitions between states, the electron either emits or absorbs a photon. So for example, if I consider this state here, n, and this state here, n, now let me call this the initial state. And let me call this the final state. In the PowerPoint slides, we call this N and M. But I think it's a little clearer if I remind you that it's the initial and the final. So if, for example, it's an initial state Ni and a photon comes in, then the photon is absorbed and it causes a transition to the excited state. On the other hand, if the initial state was up here, and I made a downward transition, then this would give off a photon of energy hf. So the initial and the final state are the labels m and n. You need to treat them with care. You need to be clear, what is the initial state? Is it this state making an upward transition, or this state making a downward transition? According to Bohr's second postulate, photons are absorbed or emitted when you make a transition between two states. So let's look at the difference between the energy in the initial state and the energy in the final state. But we've got an expression for the initial state. I just replace n by ni, or in the final state I replace n by nf. So you can see that when I put these together, I get the following expression. I'll have minus 1 on ni squared times me e to the 4 so that's the initial state, and then I'm going to subtract off the final state. So I'm going to be a little bit more careful with this. The final state would be written like this. Again, exactly the same expression, but I replace the initial with the final, the same combination of constants. And now you can see that this sign here turns this into a positive, and I can simply swap these around. And this gives me that the difference in the energy between the two states is given by me e to the 4th 8 epsilon naught squared h squared times 1 on the final state squared minus 1 on the initial state squared. Okay, that's good. We can even go further. We can get an explicit expression for the Balmer formula. Remember that this must be equal to hf, which is equal to hc on lambda. So this expression here for the delta E, the change in energy between the two states, gives off a photon of wavelength lambda of energy hf or hc on lambda, which must be equal to this. And it makes a transition from this initial state to this final state. For example, if the initial state was 3 and the final state was 2, then this gives off a transition in the red part of the spectrum, and this is the so-called red Balmer line, or the hydrogen alpha line. So I can get an expression for the Rydberg formula for the reciprocal of the wavelength. This gives me me e to the 4th on 8 epsilon naught squared. H into h squared gives me h cubed, c, and then we have this difference between these two constants. And if you go back and have a look at the PowerPoint slides, we found that this we called a constant. In fact, we'll give it the symbol R infinity, and I'll explain the infinity in a second. It's the Rydberg constant, and it can be measured experimentally. And it's roughly, 1.0 by 10 to the 7 meters to the minus 1. In fact, it can be measured with 8 or 9 significant figures, and it agrees with the predicted value to around about 7 or 8 significant figures, showing good agreement between this Bohr model and the experimental data, which gives some confidence that the Bohr model is saying something sensible about the quantum nature of the hydrogen atom. Of course, what it's saying that's sensible, it actually got the right guess. The postulate of quantized angular momentum was the key, and that holds true in the formal structure of quantum mechanics. So what we can do is we can then understand all the spectral lines in hydrogen as transitions between the initial state and the final state. The Balmer series from 3 to 2, giving the red line, or from initial 4 to 2, giving another line, which is the cyan line, and so forth. Or indeed transitions to lower states. If the final state was 1, then you can get transitions, for example, from here to here, from here to here. And these give off photons in the ultraviolet part of the spectrum corresponding to the Lyman series. So in this third part, what we've done is we've taken all of the bits that we've developed in the previous two videos, and we've assembled them to get this Rydberg formula. However, we have made one assumption. It's not a particularly dramatic assumption. In fact, because of the agreement between the experiment and the theory, the assumption is very good. But what we have is we have made an assumption, and this is the assumption that we've made. If we go back to our model of the electron circulating around the proton, we've assumed that the electron circulates about the proton. And in fact, what we've assumed is that the proton has an infinite mass. That's what the infinity here means. It means that we have an infinite mass. Now, that doesn't sound particularly plausible. So let's have a look. The mass of the proton is actually 1,836 times the mass of the electron. We're talking about the rest masses here. So in fact, it's very much larger, but it's not infinite. So in fact, what happens is that the electron circulates about the center of mass, and so does the proton. So what we would really have to describe is a two-body problem, both for the motion of the proton about the center of mass and the electron about the center of mass. We don't want to do that. What we want to do is describe this by a reduced mass. And you remember from rotational dynamics that the reduced mass of a two-body system allows one to describe effectively a two-body system by a single reduced mass. And the reduced mass, which is given the symbol m, in the case of the electron and the proton, is the mass of the first particle, the electron, times the mass of the second particle, the proton, divided by the 2. Now, if I put in the value of 1836, you can see that when I calculate this, it gives me 1836 on 1837 ME, which is 0.9995 times the mass of the electron. So you can see that the correction for including the fact that the proton has a large mass but not infinitely so is quite small. And you can now see why I could just have used the electron mass. But if I want to get a refinement to this model, I can replace the electron mass with the reduced mass. And that means that I can describe systems a little bit more accurately. In fact, what I can do is I can describe more generally what is called hydrogen-like systems, or hydrogenic atoms. So if I have not just a single proton, but Z protons, and I have a single electron circulating around, I can describe this system, this hydrogen-like system, by including the reduced mass and, more importantly, the additional charge, because instead of having a single proton, we've now got Z protons. So, for example, in the helium ion, I have a single electron, but I have two protons, in fact, two protons and two neutrons. And how do we describe this? Well, the energy that we get involving ME, when we put the numbers in, we get minus 13.6 electron volts. The way we describe this is we use the reduced mass, but as you can see, the reduced mass is going to be very close to the mass of the electrons, so that's just a small correction. More importantly, when we go through the Bohr calculation, because we dealt with the V squared, we end up with the square of the atomic number. And so this correction here, Z squared, allows me to get the correction for the to describe hydrogen-like systems. So approximately, the energy, assuming that the mass is very close to the mass of the electron, to a very good approximation is minus 13.6 Z squared on N squared. And if Z is equal to 2, such as you have with the helium ion, then it's Z squared, which is 4 times 13.6. And so this gives me minus 54.4 on N squared electron volts. So in summary, the Bohr model fits the data very well. It fits the data even better if we take into account that the mass of the proton is finite. That simply means we replace the electron mass with the reduced mass. If we want to describe a single charged particle orbiting around a collection of charges, then we do so by including the number of charges around which it circulates. So for a helium ion, we've got two protons, so there's a stronger tug of electromagnetism, and the energy then goes as Z squared times the hydrogen prediction for the energy. And these are referred to as hydrogenic atoms. In the notes, you'll see I can describe a whole range of systems, not just a helium ion, but a lithium ion, doubly charged, or a beryllium triply charged. I can also describe exotic systems such as an electron and an anti-electron, which is called positronium. In this case, just to finish, if I've got an electron and an anti-electron, which has got a positive charge, because they've got the same mass, the reduced mass of this system, which is called positronium, is actually just 1/2 the mass of the electron, or equivalently 1/2 the mass of the positron. And so I can correct. In this case, the correction for the reduced mass is significant because it's not just equivalent to the mass of the electron, it's 1/2 of it because of the fact that these are equal mass particles. So the Bohr formula applies to a wide variety of interesting systems. Of course, it is incomplete. There are many questions it leaves unanswered, such as the intensity of the spectral lines, and that requires a full description based on quantum mechanics.